In any optimization problem, what our ultimate goal is to do is to find a minimum and a maximum if we had a graphed function. And if we have a function and we took the derivative, we find that there are critical points, in this case over here, where the slope is 0, this is a minimum point, and on this graph over here, where the slope is 0, this is a maximum point. Optimization problems are some of the most common applications for differential calculus. In this example, we're given a 30 by 30 inch square piece of cardboard, which is 900 square inches, and we're going to cut off squares out of the corners to form a box. When we cut the squares off, we would fold it along this dotted line. If the squares we cut are really big, well, then we'd have a small bottom and really big sides. So this box would be super tall with a small bottom. And if we cut really small squares, we would get a really large bottom, but very small height. So what we're going to do is, using calculus, we will determine what is the maximum volume that this box can have. In order to label the dimensions on our box here, what we're going to do is we're going to label here, if these are all x's, and we're cutting those corners away, then each side height will be x, and each side will be 30 minus, and we have 1x here and 1x here, so it's 30 minus 2x for both of those two dimensions. So now, since we're going to be maximizing box volume, our primary equation is going to be volume, which is going to be a function of x, and the volume is length times width times height, or base times height times depth. In any event, it is x times 30 minus 2x times 30 minus 2x. Using FOIL, I've distributed and gotten this. I'm just going to combine like terms here. And then I'll reorder inside the parentheses. And finally, I'll distribute this x to each term inside. So finally, we have an equation which is the volume as a function of x. And since we're doing a maximizing problem, it's a max-min problem, we're going to do v prime of x, taking the derivative of this equation. So using the power rule multiple times, I get 12x squared minus 240x plus 900. Since we're maximizing volume, we want to find a maximum value on, this is a parabolic function. We want to find where v prime of x is equal to 0. Because when we hit a maximum value, the slope of this parabolic function will be 0. Now, before we continue, we have to know what allowable values of x are. I know that 0 has to be less than x, and that x has to be less than, and let's pick a maximum value here. So over here, I have 30 wide minus 2x. This can't become a 0, so this can't be 15, because I would have 30 minus 2 times 15. So our x values have to be between, they have to be positive, so they have to be between 0 and 15. So now to solve this, I want to use the quadratic formula and plug these values in. Plugging in the values from the formula, I have negative b. B is 240, so it's positive 240, plus or minus the square root of 240 squared is 57,600, minus 4 times a, which is 12, times c, which is 900. All of that over 2 times a, which is 12, so 2 times 12 is 24. Under the radical, I have 4 times 12, which is 48, 48 times 900. And then 57,600 minus 43,200. And the square root of 14,400, which is 120. And then we have to do a plus and minus. We're going to have two different answers. So answer 1 would be x equals 360 divided by 24 when we add. And the other would be 120 divided by 24 So those two answers turn out to be x equals 15 and x equals 5. Well, the problem with x equals 15 is if I put 15 in for x here, I would have 30 minus 30, so the depth of the box would be 0 and it would have 0 volume. So obviously that answer can't be used. So the correct answer would be x equals 5. But that still doesn't give us the volume. So we go back to the original equation and substitute in a 5. Substituting 5 in place of all the x's gives us 2,000 square inches. And just one final thing that I want to take a look at. If we go into Desmos, I've entered the equation for the volume of the box with respect to x, and the resulting equation on the interval from 0 to 15 for the x, we see at x equals 5 that the maximum volume with respect to x would be 2,000. So the graphing solution matches the solution we got from the optimization. Find two positive numbers that minimize the sum of twice the first number plus the second if the product of the two numbers is 288. Well, the first thing I need to know is which is going to be the first and second number. So we'll use x for the first number, y for the second number. So we have a primary equation, which is that the sum is equal to 2 times the first number x plus y. Since the product of the two numbers is 288, this gives us the secondary equation of xy equals 288. Now this second equation, I want to solve this equation to be y so that I can plug something into the first. I don't want to do the 2 times x, so we'll do the y. So I'm going to solve this equation for y by dividing both sides by x. So y equals 288 over x, and I'm going to substitute that into the primary equation. Our goal is to ultimately create an equation with only one variable in it, and then we'll take the derivative of this. And before continuing, the first thing we want to do is talk about what our domain, what are our allowable values of x. Well, this says over here that it's two positive numbers, so x can't be negative and it also can't be 0. So taking the derivative of s, we have s prime, and we'll do this in two parts. So the derivative of the first term is just 2. And then for this term over here, I have to bring the exponent to the front times 288, and I must reduce the power of x by 1. And now I can rewrite this. So I have 2 minus 288, and we'll move this back to the denominator so we have x squared. Setting the derivative here equal to 0 and solving this first derivative for the critical numbers gives us and finally taking the square root of both sides gives us x equals the critical numbers are positive and negative 12. Since the original question says that the numbers must be positive, we'll eliminate the negative solution. Taking the x equals 12 and plugging it into this equation over here, what I get is y equals 288 divided by 12. So y must be equal to 24. So now knowing the two numbers, I can substitute the 12 for x, and then I get 24 plus 24, so the sum must be 48. So what I've done here is I've gone into Desmos and I input the equation y equals 2x plus 288 over x, and it's giving me this graph of the function. There's a negative part, but the numbers had to be positive. So what I have here is a minimum value at x is 12, and the output of the function is 48, which was the sum of our two numbers, and that's the minimum value on the graph. This problem is for minimizing area. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page will be 1.5 inches, and the margins at the sides will be 1 inch wide. What should the dimensions of the page be so the least amount of paper is used? So we'll start by drawing a diagram. First, we have an inner area that contains 24 square inches of print. And then we have an outer margin, which is 1.5 inches at the top and 1 inch at the sides. So first, the area with the print, we'll label that X and Y. The base would be Y, the height will be X. So labeling the overall size of the page here, since this is 1.5 inch, this piece is X, and this is 1.5, this side would be X plus 3. Similarly for the base, it's Y for the area where the print is plus 1 inch on each side, so this is Y plus 2 inches. Our primary equation is going to be for area. So the area will be base times height. The base is Y plus 2 times X plus 3. Our secondary equation is going to involve that the 24 is going to be equal to the X times Y for this area. So we'll just write that in. So 24 equals XY. Solving the secondary equation so I can get it in terms of Y for the substitution, I'll divide both sides by X. So simplified, we just have Y equals 24 over X, and I'll just put this up in the corner. I'm now going to substitute this 24 over X in place of this Y here before I do the distribution. Multiplying the first terms, 24 over X times X, I get 24, and then 24 over X times 3, and then 2 times X and 2 times 3. And rearranging and combining like terms, I get area equals 30 plus 2x plus 72 over x. Now we differentiate with respect to x. So a prime equals, and we'll take the derivative of each term independently. Well, the derivative of a constant is 0, so I'm not going to write that. The derivative of 2x is just 2 plus, and then the derivative of this is 72 times x to the minus 1 power. So I bring the minus 1 to the front. I'm multiplying by 72, and then I reduce the power of x by 1, so it's minus 2. Simplifying on the next line, I get 2 minus 72 over x squared. So I'm going to solve this equation for x. So first thing I'll do is move the 72 over x to the left side, which equals 2. And then I'm going to multiply both sides by x squared. I then divide both sides by 2. And taking the square root of both sides, I get x equals positive negative 6, but we're going to take away the negative, so x must equal positive 6. Taking that our x value equals 6, I'll go back to this equation up here and I'll substitute instead of x here, I'll put the 6, which gives us a y value of 4. So now I can take these two values over to the page over here. Since x is 6, this side of the page has to be 6 plus 3, or 9 inches. And this side of the page must be 4 plus 2, or 6 inches. As before, let's take a look at the original area equation graphed in Desmos, which will be this one over here because I want to have it with a single variable. So here in Desmos, I've entered the equation y equals 30 plus 2x plus 72 over x, and I'm only interested in the positive x values. There is a second part to the graph down here, but we're only interested in the domain of x where we have positive numbers. And we see that the minimum value on the graph where our slope is 0, x is 6, and the y would be 54. And this corresponds to the original 9-inch height and 6-inch base, so the area is 54 inches.